Howdy, everybody. My name's RJ. I am obsessed with data graphics. The thing that's so wonderful about data graphics is that they let you see things that would otherwise be not possible as humans with just dumb eyes and slaves to time. And so data graphics, I believe, are really magical. And this afternoon, we have three speakers who are going to show you all sorts of magical things. To begin, my friend Robert Simmon is going to give us some magical views of our home planet Earth. Robert is a cartographer and science communicator who specializes in visualizing satellite data. He has decades of experience working with remote sensing experts and entrepreneurs, helping share their research and products with the public. Along the way, he's designed some of the most widely viewed imagery of Earth. Robert, stage is yours.
Thank you, RJ. So I'm really excited to be here speaking with you, and especially by all of the really interesting connections between these talks, because I think that there are threads and sort of a web of things that link them all together, and hopefully you'll be able to see that as well with mine. Especially Luca talked about a process that was widely believed to be effective in altering the weather that almost certainly did nothing. And I'm going to talk about something that almost certainly is doing something, but in some circles is widely believed not to be doing anything. And so I have 30 or so years of experience working at NASA and in commercial remote sensing, building and designing data graphics and maps that try to explain really, maybe not complex, but scientific topics for non-experts. PhDs tend to learn how to communicate to other PhDs in a lot of cases. And sometimes they forget how to talk to people without that same expertise. And so this is one of the first maps that I made that gained a lot of widespread popularity. This is the Earth at Night from 2000. And I think really the compelling thing about it is because it looks like sort of our conception of what nighttime looks like. Even though it's an impossible view, it's never night everywhere all at once, and there's clouds. And I'll talk more about that very, very soon. But it also allows you to sort of connect human impact with the natural world in a way that you don't if you're just displaying the lights by themselves. This is probably my favorite data viz that I've ever done. And it is simply 365 images taken at exactly 6 o'clock a.m. from exactly above the equator. And what it shows you is the cycles of angles between the Earth and the sun. And it's pretty much a direct method of showing the seasons, which are not caused by the distance of Earth to sun, but it's purely angle and how much light is being spread over which areas of the Earth. The last image I ever did for NASA ended up on the cover of National Geographic about exactly a decade ago in their climate issue in November of 2015. And I also like messing with people's expectations of what satellite data should look like, and also meeting people more where their perceptions and their familiarity is, rather than the rather abstract data that you sometimes get from satellites and maps. So this is Monte Fitzroy along the border between Chile and Argentina. Instead of an image taken straight down, which is the vast majority of sort of land mapping and high resolution satellite data, it's taken from about 60 degrees off nadir. So you're 2/3 of the way to the horizon. And this is like an airplane view, but from hundreds of kilometers further away. This is probably taken about 1,000 kilometers from actual Monte Fitzroy. And it's a more natural way of perceiving the imagery. Also really interested in things that are covering current events. This was a Houthi attack on Saudi oil infrastructure and the impact from that. Showed up on the front page of the New York Times and several hundred other international newspapers, and shows the power of satellite data and imagery to monitor places that are otherwise inaccessible and to show change in things that are ephemeral. And then another map that I made working with Planet, and this shows how they use their data archive to go back in time to track the Chinese balloon that had flown over the United States in early 2023, and how you had this unique signature of the way they collected their data, where the balloon wasn't just a single white blob, it was actually multiple colors. And so you narrowed down the number of images you needed to search by sort of going back through the meteorology and finding out where the air had been when you saw the balloon and go back in time, and then do a search on that area. And they tracked the balloon all the way to its launch site on the island of Hainan off the south coast of China. Today, I'm going to talk about the atmosphere and how we image the atmosphere in a way that most satellite imagery, especially in big services like Google Maps, they spend a lot of time and effort pulling the effects of the atmosphere and clouds out of the imagery, but the atmosphere is there, and it actually has a lot of really fascinating information. And I'm also going to talk about the interactions between human activity and the atmosphere and the energy that's transferred between the sun and the earth and outer space. And so this is San Francisco on a archetypical summer day, and it shows why San Francisco is the coldest place in the US in the summer. And that's because you have a cold ocean and you have a warm Central Valley, and the air is rising above the Central Valley and it's pulling the marine layer off that cold ocean and over San Francisco and over the SF Bay, and then it kind of stacks up on the East Bay Hills. And so I really like this sequence of images, which is the same day as the Sentinel image I just showed you. One image every 10 minutes, about 18 hours. And not only do you see the patterns, but you see the three-dimensional nature of the atmosphere, where especially at the end, you see these high-level clouds that are moving north when the low-level clouds are moving the exact opposite direction. And so David was mentioning at lunch that this was like one of the coldest, if not the coldest ever summers in San Francisco. And San Francisco is a place where if the climate as a whole is warming, it's actually getting colder. And so there's this counterintuitive interaction, and like maybe looking at one location in isolation doesn't make any sense, which is why you need to zoom out and look more holistically. So same sensor, this is from GOES, same day, this is the same time as that high-res view, and showing you pretty much a hemisphere. It's about plus or minus 65 degrees north-south from out in the middle of the Pacific. And it's good to keep in mind that these are not cameras, or they're not just cameras. They're scientific instruments, and they're taking calibrated measurements designed to make specific observations. And it takes some work and human decision-making to create compelling and engaging imagery from that raw data. And so they collect data in, generally speaking, remote sensing systems will collect data in discrete bands throughout the electromagnetic spectrum. And so GOES actually only has 2 bands in visible light, blue and red. And so that true color image you saw is a construction with a little bit of near infrared added back in. And so each of these bands are sensitive to different things in the atmosphere and on the surface, and they're chosen, again, very specifically to measure real phenomenon. And visible near infrared kind of works like our eyes work, where we're seeing energy from the sun reflected off the earth and then back to us and back to the camera or the instrument. When you get longer wavelengths, things get a little weird. And so this one just sees high-level clouds and cirrus clouds. This one is particularly sensitive to snow and ice, and I'm going towards longer wavelengths as I sequence through these, and you can see that in the upper right. Some measure specific things like cloud particle size. I'll do that in more detail in a bit. Shortwave window can see through the atmosphere, and here you can see like things are weird because clouds are black. So now we're starting to look at more radiated energy and less reflected energy. And then these 3 water vapor bands are actually not seeing the surface at all. Their light is being completely absorbed by the water vapor in the atmosphere, and it looks more like a gas giant than our familiar rocky planet. And you can see a similar image from GOES East, which is same instrument over the Atlantic on the wall over there. Another channel that's optimized for looking at phase, so snow, ice versus water clouds. Ozone, important gas for protecting us from UV radiation. And then these long wave bands are pretty much just temperature. And so you're looking at the radiation of the Earth, and you can see like the hot Southwest desert versus these very cold cloud tops along the equator. And so this is actually, the Earth is radiating energy back out into space as opposed to sunlight falling on it. Zooming in back to San Francisco and back to the marine layer, this is an example of how humans are influencing clouds. And so you'll notice these bright streaks that look kind of like contrails. They're ship tracks, and they're similar to contrails where they're forming these long, bright white streaks, but they're formed in a very different way. They're not water vapor being injected in the atmosphere. They're actually the result of nuclei coming off of ship exhaust. So the exhaust has particles in it, and water droplets like to glom onto other droplets or other things in the atmosphere. And so in the clean atmosphere, you get either no clouds or very big droplets that are spread pretty widely and relatively dim. And when you add in something that it can a nucleus, you get many, many small droplets. And we can actually measure the size of the droplets. We don't have to just look at this as a picture and look at the actual radius and notice where all of these streaks are. But then when you try to look at temperature, you notice that the effect almost goes away. So there's an effect on the amount of radiation, sunlight that's reflected back, but really very little effect on the energy that's radiated out. So we're changing that balance. Another way you can look at shipping, or a way that shipping affects the atmosphere, is by emitting NO2, and that's a result of burning things. And if you look, you see these sort of geometric lines in the data, and this is pure NO2 data. And then you can see how well that lines up with real ship positions. And so you can see this kind of unrelated phenomenon in a different data set, and really precisely. And so again, compare that to the NO2 data. And we're not actually restricted to just seeing things in the ocean. We can also monitor this on land. And here you see the emissions from industry, urban centers, and other forms of combustion. And then we can look at other aspects of this type of pollution. This is kind of smog that you would have maybe gotten in LA in the 70s, but spread over North India and Bangladesh. And you can see how it's kind of stacked up against the Himalaya. Again, this isn't something that you just see in true color imagery, but you also can measure it. And so this is a quantity called aerosol optical depth, which is a little abstract, but it's how far light can penetrate into this smoggy mess. Another source of aerosols, aerosol is sort of the broad term for particles in the atmosphere that aren't water droplets, is smoke from agricultural fires. So this is the southern Amazon from last year, which was a particularly bad burning season, mostly due to a particularly dry season. And then we can zoom in. And here we can not just look at the smoke plumes and maybe the origins of individual fires, but we can see the influence on the forest where you have these brown, gray burn scars. And we can look at how that's changing the energy balance as different amounts of sunlight get reflected. Aerosols aren't just man-made. We also have natural aerosols. One example is volcanic ash. So this is a volcano in Peru. Another is dust. So Lubbock, Texas, late winter, early spring of 2024. Nice clear day. About a year later, this was a dust storm that covered a good part of Oklahoma and western Texas and probably Kansas as well. And this is something we can monitor worldwide. And there's even ways to tease out those differences between man-made and natural aerosols. Man-made aerosols tend to be small, so fine particles, and natural aerosols tend to be large, so coarse particles. And so where there's red, these are more man-made, and where it's yellow, it's more natural. And we look at this globally. And of course, you need to look at things globally because these systems are all connected, the atmosphere is connected, the oceans are connected, and when you're looking at energy balance and the difference between the sunlight and the energy and the heat that goes out, you need to look at it globally and you need to look at it over time. And so we're really interested in this because we know that we are burning fossil fuels and we are generating greenhouse gases. And so this is the familiar graph from the Mauna Loa Observatory that you've all probably seen this, where we have a long-term trend and then a sawtooth seasonal trend superimposed on it. And this is from Mauna Loa Observatory near the summit of Mauna Loa on the Big Island of Hawaii, about 3,400 meters. And I like this image not just because I'm fascinated by volcanoes, but also because it's a reminder that satellite images and satellite data are also maps. Generally speaking, we know precisely where every single pixel is. And so you can overlay something like a contour map to gain more insight into the image. Okay, back to this. As I said, you've all probably seen this, but what maybe you haven't seen is the rest of the network. And so here we have a station on the north slope of Alaska that I cannot pronounce, but used to be Barrow, and the South Pole. And all three of these stations are generating the same long-term trend, but there's a huge seasonal component in Alaska and almost no seasonal component in the South Pole. And why? And that is simply because there's more land mass in the northern hemisphere than there is in the southern hemisphere, and land plants absorb and use up more carbon dioxide than water plants do. And so in the northern hemisphere summer, you get a huge drawdown of CO2, and it goes into the plants and it goes into the leaves and the grass and the wood. And in the winter, some of that CO2 is released back into the atmosphere. And so you end up with a pretty strong seasonal cycle. And so at the lower left there is what happens if you take out the long-term trend and just look at the annual variation. In the daily data set, you see this nice curve with high levels of CO2 in December, January, February, March, and then low levels July, August, September, and then it kind of ramps back up. And because of this location-dependent aspect of it, we not only need to look in time, but we need to look in space. And so this is from a satellite called OCO2, and it's a 7-year record of global CO2 every month. And the thing that I find most fascinating about it is that the highest levels in January of 2015 were much lower than the lowest levels in January of 2022. And so we are pumping a tremendous amount of carbon dioxide into the atmosphere. And one of the ways that you can look at the effect of that is by measuring temperature. If you're stuck on land, you would do that with a thermometer, and it turns out we've been doing that almost as long as we've had thermometers. So this is something called the Central England Temperature Data Set. It is a collection of several different stations in Central England, obviously, and it goes back to the late 1650s until today. And so you can see where the trend was pretty stable up until 1950, 1980, and you've gotten sort of an outlier of warm years since then. And as I said, that's one way of looking at things. But planetary heat uptake accounts for the entire energy added to or removed from the climate system. And this is arguably a more fundamental measure of global warming than global mean surface temperature. And so this means if we step back and we go from space and we look at that energy balance, well, maybe you get not a more accurate, but a more definitive picture of global warming and global climate change. And again, it kind of goes back to what I was saying about when it's warm in the Central Valley, it's cold in San Francisco. And so looking at the temperature record can be misleading. Scientists know that phenomenon, and they know how to correct trends and differences between different thermometers. But there are ways to complement that and get a completely independent measure of what's going on. And I'll step back and explain energy balance a little bit. So I really like this photo from the International Space Station. It's something I didn't take. It's one of the few images in this presentation that I didn't do. But I really like it because it shows you many aspects of what's going on. It shows you the relationship between forests and clouds, where this is the Congo Basin, and the rainforest is actually exhaling as it photosynthesizes, and it's releasing water vapor. And so you got really thick clouds over the rainforest. Where there's rivers and there's no vegetation, there's no clouds. And that's because there's no respiration going on. You can also see these thunderstorms along the horizon, and they're moving energy from ground level up into the upper atmosphere. And they're, strong columns of rising air. And when it condenses in the upper atmosphere, it's actually dumping a ton of heat in the upper atmosphere. So that's an important way of moving energy through the atmosphere and moving it up and closer to space. And then, of course, you see the veil of the atmosphere and how thin that is, and how close we are to space. Here's a diagrammatic way of looking at energy balance. So essentially, you're worried about the difference between the energy coming in on the left and the energy going out on the right. And so the energy on the left is mostly visible light, and the energy on the right is mostly heat. So sometimes you'll hear them referred to as like shortwave and longwave radiation, but I think that's a little confusing. But you can look at this systematically from space with an instrument called CERES, which stands for Clouds and Earth's Radiant Energy System. It's actually at least 3 different instruments on 3 different satellites. On the top, you have incoming solar energy, and this is totally determined by geometry. Next, you have reflected sunlight, and this is affected by clouds and brightness. So you can see like the Sahara is brighter than the mid-ocean or the boreal forest. And then emitted heat. And so that's thermal, long wave, just temperature essentially. And then the difference between all those is net flux. And so you have the equatorial regions are absorbing a lot of energy, so they're pretty red. And then the polar regions in general are emitting more energy than they receive. And so they're bluer. And again, we can look at this over time. So this is climatology data. So this is actually the mission long average for each of these months. And you can see these seasonal patterns, which, all the way back to the Meteosat sequence in the very beginning showing the Earth's tilt. Now, if we look at that over time, and we've got 25 years or so of data from CERES for now, it doesn't look that interesting. You see mostly seasonal cycle. But if instead of plotting everything together, you plot 2000 to 2025 for January, 2000 to 2025 for February, et cetera, you see that there's an upward trend in every single month. And so this is a signature, a fingerprint of the impact that greenhouse gases are having on the climate. So we know that they're changing the energy balance. And when it's out of balance, when we're, and it's going up like this, we are due future temperature rise. And so it's an independent way of measuring what we already do with thermometers. And then finally, this is the probably most familiar image that I've made. Ended up on the iPhone, was this summer sold at IKEA on a poster. It's been on the side of Berkeley recycling trucks. I thought that was a really cool use of it. And this image, even though it's more than 20 can drink, that image can drink, is the result of what is now 60 years of effort into studying Earth's climate from space, led mainly by the US. And that is a process that honestly is being wound down right now. So sensors are being decommissioned, websites are being shut down, scientists are being laid off, archives are being closed, and that was not supposed to go to that image. And it really makes me sad, and I would love to try to, bridge the gap until things improve in the US. So if you know of anybody who's interested in doing that type of thing, I'm connected with people at NOAA and NASA, and it's something I really care about. So thanks very much.
Questions?
Okay, if we sent a satellite into space that wasn't for science but was for science education, what wavelength would you add? Or what type of sensor would you add that you don't have to play with right now?
Oh, that I don't have to play with. I like higher res, higher quality. Like I don't really know what wavelength would be missing but like if we do the current wavelengths at higher resolution, higher frequency, more public, less copyrighted for the high res stuff. And like I like obliques, and very few people are really interested in doing that, even though there's some really interesting applications for it. So I just more better, more than specifically different. Like I'm sure there's scientists out there who'd be like XYZ, and like that's their thing. But I'm more like, how do you inspire people? How do you, you know, how I stuff that I get excited about, I kind of think other people will too, and that's basically how I do it.
Hi, that was such a cool talk. Thank you so much.
You're welcome.
Some of the first images in the presentation, which I've obviously seen before, I actually never realized like how much deliberate effort goes into what elements of the image you want to highlight. Like I think you showed one where you kind of explained that like the cloud patterns you saw over the Earth are not obviously just visible there. You have to like, I don't know, it was like you have to overlay the element, or you have to sort of like you decide what kinds of things you want to display on an image. And I feel like I've never thought about that in the context of like, I've thought about that a lot in the context of geopolitical maps, but not really weather maps. And I'm curious in like the course of your career, if there have been difficult choices around, especially in like a news or science education context, where you felt like the particular things you choose to highlight in an image are like how much do you have to deliberate over whether that feels honest to a viewer who might just look at the image and imagine that that is just, you can just take a raw photograph and it looks like that. You know what I mean?
Constantly.
Yeah.
So for scientific stuff, you really want to make sure that what you're saying is happening is what's actually happening. Like when I did a dry run with this with RJ, I was talking about the Amazon and talking about how political change has, with Bolsonaro being replaced by Lucas, I think Lucas is his name, but the political change that they're now cracking down more on deforestation, but that was actually much more of like a climate-driven change between 2024 and 2025. And so like you go up and you look for contextual stuff. Also, when I worked for Planet, we did a lot of very high resolution imagery of the war in Ukraine. And we needed to be conscious of not giving away information that would possibly be an advantage for the Russians. And so that's kind of picking sides. I guess maybe a more neutral one is like if you have a refugee camp, you want to make sure that you're not exposing information that the people who are driving those refugees away would take advantage of. And yeah, I really want to be true. I now am, and I tend to be more on science communication than like current events type stuff. But in both cases, you really need to be in a conversation with experts and make sure that your interpretation is correct. And I've screwed up before and had been corrected. But like, hopefully I'm very happy to receive that criticism.
It's a great presentation. So it's a follow-up actually on Brazil. Lula is the president. And is it possible to really know what part of, for example, these NO2 particles, or through the satellite imagery, which things are man-made and which ones are natural phenomena, or even in things when you showed Bangladesh, something about also almost like the distribution, you know, who gets kind of the emissions produced by someone else and gets affected by them, or even, I think it was Mongabay, I don't remember who it was, but in Southeast Asia, they've been doing all this satellite imagery of illegal roads for logging into the rainforest. So can you get to that point where we can actually show agency and the intentionality and who's doing it?
I think you can infer intentionality. You can't necessarily prove intentionality. I guess one example would be, again, at Planet, we were doing these maps of all of New Mexico, and then they were using it to demonstrate like when roads and when wells were built, and checking when permits were issued. And so you could prove that like something was built before the permit, but you need to combine this stuff almost always with ground knowledge. Like you can make a lot of claims and sort of make your own narrative by looking at these, but you really need that expertise to understand what's going on. And so like, usually this would be one piece of evidence. But like, yeah, you can totally see like a gas flare or something like that. And you would know that that was the person who owned the well that was located at. Like, it couldn't be anybody else.
we're going to move into our next presentation. We're tight on time. Hopefully, yes, thanks. Thanks, Rob.
Angel Abbud-Madrid is the director of the Center for Space Resources at the Colorado School of Mines, where he leads a program focused on the human and robotic exploration of space and the utilization of its resources. He has more than 35 years of experience in space projects, including experiments on low-gravity airplanes, a space shuttle, the International Space Station, lunar and planetary missions, and he received the NASA Astronaut's Personal Achievement Award for his contributions to human spaceflight. You know, with Rob, we saw how sensors can be sort of pointed, you know, at the Earth. Then we saw how sensors can kind of be pointed out. And I think that Angel is really going to give us a great cap to these to this three-speaker panel, because what he's going to do is actually take a step back over time and show us a long arc kind of story about how we develop the ability to construct these kinds of views. So please join me in welcoming Angel.
Thank you. Thank you so much for the introduction and for the invitation to be at this very unique conference focusing on above and below, and for the unique opportunity to be in front of two individuals whose websites completely use my free time, I have to admit. David Rumsey, that has the most advanced technology to look in detail of all the maps that that I adore, and Barry Ruderman, that bombards my email inbox with attempts to acquire the maps that David Rumsey has on his website. I think it's a match made in heaven that unites my higher thoughts above to my pragmatic reality below. Now, when I was invited to this talk, I was asked to focus on everything except the surface. But I will venture to say, and maybe I'm biased by my profession, that the below, the surface, and the above are all intimately connected, and they all benefit greatly from the advanced technology that we have developed from above. And this thought, and this has been proven by all the speakers before me, and you will see it from the ones that will follow. And this thought came to me from a flight that I made from Denver to Europe, in which I was looking at the landscape, the coastlines, the oceans, and I kept thinking about this phrase that I had heard somewhere, or this quote, that said the following. It said, "Man must rise above the earth to the top of the atmosphere and beyond, for only thus he will fully understand the world in which he lived." And I kept thinking, this has to come from the early astronauts from the 1960s that have been able to go out and see the world from up above. And when I landed and Googled it, I was surprised to see that this is a quote attributed to Socrates, 400 years BC. A fantastic and remarkable thinking at the time that he didn't have the technology to get up above, and we were just starting on Western philosophy to understand the world in which we live. And so what I decided to do is to come up with a step back and take a general look at how is that we got to where we are in terms of advanced technology from above, to understand all the things that have been presented here and the effort that it took to get to this point. So that we can understand where we are at this point. So what I want you to do now is fasten your seatbelt. Okay, ready? We're going to take advantage of this fantastic spacecraft, the David Rumsey Center, in which we're all going to be as we launch, as we start rising in terms of space and time, to look at the evolution on the major milestones and all the developments that took us from below the surface all the way up above, and that has given us that incredible ability to map all aspects of below the surface and above. So let's start by going back in time to the first mention of what it would be like to see the world from up above, and that comes from the myth and the legend of Daedalus and Icarus, which all of you know. Like all of those myths, it starts by there was a king, and this king was afraid of this beast called the Minotaur that was terrorizing his population. And so he decided to call the best architect of the day that brought his son Icarus. It was bring your son to work day. And he was told, you have to design this labyrinth which will contain the Minotaur. And he started doing that. And he actually created probably the first map ever in the history. Obviously, it's a legend. But in which you could see exactly how to get to the Minotaur. And this map was so valuable that he was locked with Icarus so that they couldn't reveal the secrets. This is pretty much like the Spanish Empire for 300 years that locked all those maps of America so nobody could see them. And so he decided, how are we going to get out of this? Well, maybe we try flying. Nobody has done that before. And he said, well, if we can attach some feathers to our back, maybe we can go up and escape from this place. And so he tried it with Sun, and he said, when they were ready, he said, Sun, we're going to go out. You're going to be accelerated when we go out. So please try to not to go too fast or too high, even though you're going to be very excited. And like any obedient teenager, he did exactly the opposite. So he started flying faster and higher. He saw Crete and the Mediterranean. He was excited to see things from above. And then the sun burned the wax on his wings, and he fell to his death. So this is a myth and a legend, but it shows the duality of two things of humans, and we all have this. One part of us wants to risk and go beyond the edge to see what we can do, and the other one tries to hold us back and keep it safe. And we'll see this through the entire history. Now, the first attempt to build something that would fly comes from Archytas of Tarentum that put together this thing called the pigeon. He put this bronze figurine with water, heated up, steam came out, and was going around and around, held by some wires from the ceiling. And his peers was just laughing at him. Said, Archytas, you can try all you want. We will never be able to get out and fly because we're human. We're bound to be here. And efforts to fly pretty much stalled for centuries. What didn't stop us is this insatiable need for humans to map its surroundings and name everything around us. And an example of that is this map from Isidore of Seville of the 7th century that was printed for the first time in 1472. It's a TO map of the Etymology Encyclopedia that is considered probably the very first printed map of the Western world as known in the medieval times. And this was done at a time that we couldn't see things from above. But he nicely captured all the continents, Africa, Europe, Asia. He even assigned them to the different sons of Noah. He had on the T the Mediterranean, and then he had the big O, which is the ocean that surrounds the world. So this was our view without even having the view from above, which was pretty good back then. And so we couldn't design anything at that time, but we needed first to crawl and then walk and then run. So we started with the dreamers, people that can dream about what would be possible. And that started, not started, but this is an example, Lucian of Samosata, that came up with a science fiction called True Story, in which didn't have anything that was true about it. But there was this spacecraft of the time. This is the most advanced technology of the time, a ship that will go up and meet some of the people that live there, the first mentioning of aliens. Johannes Kepler, that we would see, this is one of the greatest figures in the scientific revolution that came out with the planetary laws of motion. But on his spare time, he actually wrote science fiction, and he wrote this book called Somnium, in which, again, he imagines a ship that is taken up by a kite. And in there, people could actually see below. In fact, he mentions the telescope that was just recently invented, and he could see below, so people could see below with all the details. Then came Jules Verne, that imagined a trip from Earth to the moon with a spacecraft in different stages, a capsule that was aerodynamically shaped when aerodynamics was not even invented, a trip that will depart from Florida and will have 3 men on board. Wouldn't you know that 100 years later you will have a ship in 3 stages with an aerodynamical capsule departing from Florida with 3 men on board. He even described the exhilarating feeling of these people floating around in zero gravity with much nicer suits and more formal, and what it will feel like that. Something that also, after 100 years or so, not only astronauts get to experience, but also human beings that conduct experiments on parabolic flights. Like these 3 men that tried to replicate Jules Verne, and they started working on their experiment. And at some point I got carried away and I told my colleagues, hey, say hi to the David Rumsey Center. They have a great conference right there on Above and Beyond, okay? And now go back to your work and do the experiments that you have to do. So as you can see, those thinkings of Jules Verne became true in many ways. And so now we pass to the thinkers. Now we needed to inject some scientific knowledge in order to achieve this. And first, we needed to look at the map. Where is that we're going before we actually invent all these gadgets in order to fly into space? This starts with Claudius of Ptolemy that puts together his map of the solar system, of the universe known back then, with the Earth in the center. and all the planets going around, and all the planets going, and even the sun going around, and then the firmament up above. Great way to look at the Earth. In fact, it's a good way. Today we even talk about the sunrise and sun setting, which is not true, but we still go by Ptolemy. But the problem was to relate his model with observations. In order to put the Earth in the center, he had to then do something about the retrograde motion of Mars. So he started devising these funky trajectories of Mars and then Mercury and Venus in order to meet observations with theory. Complicated map of the universe, but it somehow worked for him. But it had to be simpler than this. And for that, we needed Copernicus, that in this nice painting is shown with his map, the new way of looking at the solar system with the sun in the center and all the planets going around. And then all of a sudden, things started fitting nicely. All these planets will go around in circular motion around the sun, and you will have even the exterior or the outer planets, Saturn and Jupiter, also going around the sun. It was great, but not quite right. We needed more. Tycho Brahe came up with the most accurate measurements of the stars and position of planets and the like. He had all the funding from his king of Denmark. He even had an entire island made to him to do this work, something that researchers these days will salivate having something like this. So he had all the funding of the world, and he was able to measure, and he said, there's just by arc minutes and arc seconds, the circular motion doesn't fit with the measurements. So we needed something else. And that came to Johannes Kepler, the same one that had this science fiction. He was put together the planetary laws of motion. And in a few words, what he did is said, maybe we can correct it very simply. We can go from circles, circular orbits, and just to squeeze them into an ellipse. And all of a sudden, everything made sense. Now all the measurements and the observations could fit nicely. We had our first map of where we were planning to go in the future. But we needed to understand the why. Why are planets doing what they're doing? Why are they going around in this type of orbits? And for that, we needed another great mind of the scientific era, the scientific revolution, Isaac Newton, that came up with this concept of gravity. Gravity that can explain his laws of universal gravitation and can relate the attraction between two bodies inversely proportional to the distance squared to them. And all of a sudden, it all started making sense. Why the things are where they are. You can accurately know where they can come from for all the planets, not just the moon. And we can even use that, and we use it today, to understand what other planets are and how they move around. So it was a great contribution from Newton. In the middle of all this was Galileo Galilei, which was mentioned nicely by Juna before me, that he had the ability to use the latest instrument of his time, the telescope. And instead of focusing on ships and looking at birds or the neighbor's house, he pointed it to the stars. And he saw for the first time on November of 1609, the most beautiful sight of the moon, and also the most imperfect one. He looked at it and said, contrary to Aristotelian thinking that the moon and all celestial bodies were round and perfect, he saw that it was not that way. He described it as uneven, rough, full of cavities and prominences, very much like Earth. So he was able to see very nicely how it looked like. He describes all the mountainous ranges. He even talks about things that Kepler later on talked about, those dark regions and those white regions that Kepler named the mare, because he thought it was seas or oceans, and then the terra, the land. Galileo didn't think that this was oceans and land, but that terminology stayed with it. It's a great description. This is a watercolor that he made on November of 1609. Realize what it takes to do that. In fact, just to prove to you how accurate this is, about 2 weeks ago, I waited until the moon was on this face. And I took a picture with my camera that is far superior for the 2-inch telescope that Galileo had. And this is what I saw. So take a look at what we see here of the big crater, the craters in the middle with the terminator, the dark and the white regions. And this is what I observed with my camera. There you can see the big crater, the mountainous region. I didn't have to move the arrows where it shows the dark and the white regions. This is an amazing view and description that Galileo had from way back then. and shows us how we were able to observe the moon first before we were able to map it. This is contrary to what we had on Earth. On Earth, if we have to wait many years before getting out, here we could see it, and that prompted everybody to start mapping every feature that and name it after this. And here is an example of two systems that were used for nomenclature, because there was a lot of confusion back then. This is from an atlas from Homan, the same Homan where that drawing from the beautiful office of Evan comes from, the same atlas. But here he put the two most popular nomenclatures, from Hevelius and from Riccioli. And both of them agreed that, and they painted the two shades, the dark and the white, so the two areas that Kepler had named, the mare and the seas, that actually turned out to be not oceans. You can actually see some samples on that exhibit that Christina put very nicely over there, where you can see that the dark part is basaltic material. This is lava that came out and filled all these impact basins that were created by meteorite impacts. And the other one is an orthosite material. This is the terra, the primordial crust of the moon. And that's what they were able to observe as the dark and white. And they all agreed that that was painted that way, but they differ in terms of the nomenclature. Hevelius decided that this should be named after Earth terrestrial features in Latin, very complex Latin. Whereas Riccioli said, let's name it after astronomers and the moods of weather. And Riccioli actually was the one that won the race. He was able to name, put some of the names that we still use today. You have Mare Tranquillitatis, the Sea of Tranquility, where we landed in Apollo 11. Also in 1969, the Soviets tried to land at the same time of Apollo 11, but they crashed on Mare Crisium, the Sea of Crisis, very aptly named, even 400 years before. He put his Copernicus, who was a very controversial figure back then, and he put it on Oceanus Procellarum, the oceans of storms, because of the stormy controversy. He even named a crater after himself, Riccioli, and he even allowed his competitor to have a crater. There's Hevelius on the Sea of Hotness or something, because there were hot figures back then. So there you can see how we, as soon as we observed it from above, we were able to map this in very much detail. And this is the nomenclature that pretty much stays up to today. All right, we were at this point, and it was time to go to the doers. It's time to make things happen, to get out and see the world from up above. Some of the first efforts is by the Montgolfier brothers that come up with a device, a balloon that can be, had hot air in one end, and that hot air was going to rise and pull it up. And with that, he was able to make demonstrations, very popular ones, where people were looking at this wonderful new flying machine. They tested some animals at first, but finally we decided to send humans in November of 1783 in the Chateau de la Muette that you can even visit today. It's outside Paris. And there, the first human being went into space, went into air. He became the first aviator, let's say, Jean-François Pilat de Rosier, who actually died a year later trying to cross the English Channel. He became the first casualty of air travel, but that's a different story. So that was the first attempt. But at this point, we needed not just a way to fly, because then we will have to rely on what Jean-François will tell us about what he saw. And as we know, humans can lie heavily. And so we needed to record this with some type of medium so that it could be something that it can be objective. So around the same time, a few decades later, comes photography. And with that, with the efforts of Louis de Daguerre, we start now recording what we can see. These are some of the very first high views from the apartment of Louis Daguerre, where we can see now how things look below. In fact, this is the very first picture where you can see a human being. This took several seconds to take. The exposures were long. But this guy was shining his shoes, and he stayed quiet for quite some time, and we were able to capture it. We don't know the name or anything like that, but that's the first view from above. And then after that, you started putting together balloons and photography. And with the help of Gaspard Nadar, he became very popular, taking pictures from up above. Unfortunately, we don't have any of those pictures, so it fell into James Wallace Black to become to take the very oldest surviving aerial photo in 1860. This is Boston, and he describes it as the eagle and the wild goose see it. Now we can start seeing a truly bird's eye view. And this is a very powerful, it may look a simple picture to you, but this was very powerful back then. We needed to keep going. And remember Archytas with his pigeon, and though everybody laughed at him, well, similar technology was invented where pigeons carry on board a camera. And they were set out to take pictures, mostly of wealthy people that wanted to take their big states, as you can see here. But you had some problem. You have the feathers of the pigeon right here with no means of cropping it or making it look nice, but a way to start taking pictures. Remember our friend Kepler that talked about a kite lifting us, and so we can see the world from above. Well, there was in the early 1900s kite photography, which, by the way, took one of the best pictures of where we are right now in San Francisco, right after the earthquake, a picture that served to evaluate the damage and then help on reconstruction. So you can see now the power of lifting ourselves more and more. Now, at that point, we needed to go just from one place to start seeing it in a more continuous way. And that's when the first flight occurs. It's a few seconds, but then we start traveling longer. We start incorporating photography in First World War on board airplanes, so we can see below. And now we have some of what's been described, the overview effect. You can even see the future because you have your troops, and you can see that the other ones are going to come and hit them without them knowing. So you can even alter the future by letting them know what's happening. The power of seeing things from above. We needed to continue going higher. Remember Jules Verne? Well, we have Robert Goddard in Massachusetts that came up with the first liquid fuel rocket. And on that, he put a camera inside and was able to take some of the very first photographs from rockets. Very low altitude, but at least he showed his town of Auburn, Massachusetts. We needed to go higher. And for that, we needed war again. And World War II brings us one of the most advanced rockets, the V-2 rocket, that was used by Germany at the last stages of the war so that they could launch him from Germany all the way up to London to scare the population. They were not very accurate, but they definitely caused a lot of terror. And so this thing continued, and the rocket team was brought, most of them were brought to El Paso, Texas, in Fort Bliss, and they went to White Sands to make some of the tests, to mainly look at rocket performance and the like. But there was an engineer that said, well, while you're doing this, why not put a camera on top of it? Everybody laughed at him. Why would you like to have a camera? Yeah, we're going higher and higher. Can I just make use of a camera? And say, all right. He got his wish. He installed a camera in one of those V-2 rockets in October of 1946. And there it is, the rocket going up. There's a camera below, but then the camera started rolling about 1.5 frames per second, and it started recording below all the landscape there of New Mexico. When it got to the top of the parabola, it started then tumbling a little bit, and then you can start seeing the contrast between darkness and the edge. And with this, we were able to finally see the difference between space and Earth. And this became the very first photograph from space of 1946. Imagine, I mean, it's low resolution, grainy, but the power of this, and I think Clyde Halliday saw this when he mentioned that he turned around to his team and he said, do you realize what's going on here? The entire land area of the globe might be mapped this way. 80 years after that, we have all the mapping of the world that we want from Global Positioning System, all from these efforts over here. So again, we tend to forget those type of things. Then we kept going. And now it was time for humans to go out and not just see the curvature, but see the entire globe. So the astronauts of Apollo 8 were launched in December of 21 of 1968. They went around the moon for about 3 times. They were there just to mainly take pictures of the moon, not to land. But on the 4th orbit, the commander, Frank Borman, turned the spacecraft around in such a way that after coming around on the 4th orbit, for all of a sudden, the 3 astronauts, and later on the entire world, were able to see the Earth rising above the horizon of another celestial body. A powerful image of the Earth from the point of view of the moon. And this showed us the Earth just beautifully floating in space, borderless, uncharted, unrestrained by any constraints of humans trying to make divisions and name things and all that. It was just like that, as natural as possible. This became one of the most widely distributed images in the history of photography. It inspired the environmental movement. It even forced the students, forced the astronauts when they came back to say, we went out to explore space and came back knowing how to look at Earth. It was a very inspiring moment. And it happened on December 24 of 1968. Let's now compare that first look at Earth from Isidore de Seville without having any advantage of the view from space, and now the view from Earthrise, that picture, and try to compare to see the similarities, but also the big differences. For this, I'm going to do something like Rob did, manipulate the image a little bit, turn it around. It's being processed to remove a little bit of the clouds. Sorry about that, Rob. So that we can see the continents and see the comparison. Now we have east on top, and you can see the western part of Africa, just as it was described by Isidore on this map on the right. Europe is hard to see because there are clouds, but there's Europa right here on the Isidore's map. Asia, you cannot see it because not only the moon is there, but the terminator obscures that. But something that is not on Isidore de Seville's map is a totally new continent, South America, that if we had had the possibility of seeing it from above, just like we saw the moon first, we have been able to include it and not spend hundreds of years trying to map the Earth up above. So this is where we are at this point. And now we continue going. Look at Mars. We observe it, and we have plastered the place with all sorts of names of volcanoes, of canyons. We have even created the most accurate geological maps, even better than the ones that we have from the oceans that I think, what's her name? Sydney, I think, beloved? Yeah, no, Betsy said yesterday. And then we kept going, mapping all sorts of planets in the solar system, even a planet that is no longer a planet. Pluto that has been demoted to a dwarf planet, we have named the volcanoes, the ice features, everything. So are we going to continue just going and mapping? Is the fun over? Well, not really. Because just like on Earth, we were trapped inside of it, and we were only able to imagine what it would be like to form above, so we are trapped inside of our mother galaxy, the Milky Way. And like Juna showed very nicely, now you can, this is one of the most highest resolution ones. You can see billions of stars. You can see bright nebula. You can see the core of it. But we're trapped inside. We can only see it sideways. And just like on Earth, it would be great if we at some point can go out and see it from up above. Some efforts have been done. This is probably one of the best maps, came up this year from the European Space Agency, of how it would be like to see the Milky Way from above. It even plastered the place with names, arms, and the bulge here. Even puts our sun here. This is where we are, in the middle of billions of stars, looking at the galaxy from sideways. To the point that we are asking ourselves, well, what's on the other side? Can we see through this bright spot and understand what is out there? That's what's called nowadays Zona Galactica Incognita. Just like Terra Cognita was named in those maps of old. So what's on the other side? And June again mentioned all the possibilities. Could we have any new galactic features? We can see with a lot of observatories, but we don't really know. Could it be that this is what we see? Nothingness, dark matter. Yeah, astrophysicists like Juna can say, well, maybe we can figure out ways to see how light and matter interacts with gravity, but is that mapping? Is that what we do nowadays? Not really. So challenging, yes, but imagine the excitement of David Rumsey when he can use all his advanced technology to map this, nothingness. And the staff of the David Rumsey Center, that they can have decades and centuries to catalog things that we're going to be mapping new. And Barry Ruderman selling nothingness for thousands of dollars. This is truly exciting. But at this point, we got to stop. I have 1 more minute to go, and we have to make all our way from dark matter all the way back to Earth. So let's start our descent. And let's start on this David Rumsey Center spacecraft, going through galaxies and going through the billions of stars and galaxies, and finding our own mother galaxy. And inside our mother galaxy, look through the billions of stars and finally go through our solar system, where we can go through all those planets that we have mapped before. We have Saturn, and we have Jupiter, and we have the asteroid belt that we have also named. We have Mars that we have mapped geologically in exciting ways. The moon that was observed by Galileo in 1609. The curvature of Earth that we broke in 1946 to finally see the curvature of Earth. All the clouds around, and finally see there the below, the oceans and the land masses. And there in the distance, the place where we started 30 minutes ago, the David Rumsey Center in the middle of Stanford University. And now that we have arrived, let's reflect on that phrase that I mentioned at the beginning from Socrates and realize how true it was. That in order to capture understand the world in which we live, we need to go to the top of the atmosphere beyond and see how the view from above can give us information on the below, the surface, and then destinations beyond our own. And what better place to continue the discussion than in a conference called Above and Below. Thank you much.
We've got time for one quick question.
One quick question.
Who's it going to be?
Juna, oh my God, an astrophysicist. I'm in trouble. Okay.
I just have a comment that the map of the dark matter will cost billions of dollars.
Barry, you ready? And Alex? Yeah? Okay.
Awesome. Well,
Let me say just one more thing. It has been mentioned by several that all of their work has been published in National Geographic because how great it is. How great could it be a conference of Above and Below when the latest issue of National Geographic that I received by my home 2 days ago has an article called Above and Below, a sign of great things that has been done here. Thank you so much.
thank you, Angel.